So let's talk about ionization constants and water's role. So ionization constants, these are going to be the same thing like we talked about with equilibrium constants. They're just specific to the equilibrium we're talking about. So the equilibrium, remember our double-headed arrow, equilibrium. But the equilibrium we're talking about specifically is when acid ionizes in water. So we're just talking about a very specific thing. So that's why it has its own little name. But don't think this is really anything new. So what's happening is my acid with my water, since it's an acid, it wants to separate and make my ions. So think about H plus and A minus. But the H plus is in water, so it becomes H3O plus. So here we're going to talk about the acid ionization constant. Okay, so this is going to be used to tell me how strong of an acid is. Remember we said that the bigger it is, higher it is than 1, the stronger the acid. So the stronger, the larger the Ka, the stronger the acids. We kind of noticed this when we did our trends. The weaker acids are going to have small Kas. So let's talk about how do we write it. So it's Ka, so just like our equilibriums with Kc and Kps, and remember it's going to be my products over my reactants. Same thing we did last chapter. So let's look. What are my products? This guy's aqueous, so I include him. Concentration of H3O plus or H plus. He's aqueous, so I include him. Divided by, he's aqueous, so I include him. He's a liquid, so I don't include him. Okay, so that would be my Ka. Concentration of my H3O plus over my base conjugate over my acid. So acid, base conjugate, H3O plus. Okay, so that's our Ka. That's how we write it. Now we're going to talk about Ka a lot more in this chapter, but I wanted to introduce it to you here. Now let's talk about water. You see how everything's in water because it's an acid and I've got water everywhere. So let's talk about water's role specifically. Water kind of can do this like dual personality thing. So water can act as a base when an acid is dissolved in water. So for example, let's look, his partner is with him. So he's going to give up the H plus to the B, he's going to lose an H plus. So you have just the Br minus. So if he loses H plus, he's the acid. If he's the acid, that means that the water is going to act like the base. And you can see because he's going to gain the H plus to make H3O plus. So you have an acid, the water acts like a base. But water can act like an acid when some bases are used. Let's look here. NH3, who's his partner, NH4 plus. What's happening between here and here? He's going to gain NH plus. So that means he's the base. What does water do? He's going to lose NH plus. He's the acid. So in one case, water's a base. In another case, water's an acid. How can it swap? I gave you those tables at the beginning. You said these guys are acids, these guys are bases. I didn't say they could swap. Water is special. Water is what we call amphiprotic, meaning it can donate, or accept a proton, meaning it can act as an acid or a base. Either one. It can act as whatever is kind of needed based on who he's partnered with. All right, now let's look at something that's important that underlines our issues with just everything being in water. So since everything is in water and water can act like an acid or a base, water molecules can actually react with each other. So you could just have a bunch of water floating around and it can react with each other. Because one guy can act like a base, one guy can act like a water. So this idea, one can act like a water, sorry. One water can act like a base, one water can act like an acid. I wrote it right, I said it wrong, but I caught it. So these guys can react with each other. This is called autoionization. Okay, because they're automatically going to react with each other and ionize. So if he's a base, what's he going to do? He's going to gain NH+. So his partner is the H3O+. Acids lose their H+, so his partner is the OH-. So he's the base, he's the acid, he's the acid, he's the base. Conjugates. Now, just like that, we can also write our ionization. But since this is water, it's not the ionization constant for acid, because there's no real acid here. This is the ionization constant for water. So now this would be Kw. So how do we write the Kw? Products over reactants. So here's one of my products. It's an aqueous, so it counts. Here's an aqueous, it counts. Here's liquid, here's a liquid. So it's just Kw is equal to H3O+ times OH-. This is how they relate. Okay? Now, the equilibrium, this equilibrium, is very reactant favored. Okay? So you're not going to get a lot of it happening. It's a really, really small fraction. So whenever we're trying to calculate how much acid or base ions, like how much H3O+ or OH- ions are present, we don't actually have to worry about the fact that some of it might be coming from the water versus from the acid or the base. Okay? So we don't worry about this in the sense of like we have to calculate this in. But this relationship is really important. And this is one of your equations. Because this relates my acid created ions from my base created ions. Now, we can actually figure out this K. Now, remember last chapter, we talked about how Ks are temperature dependent. It's the same thing here. Like all equilibrium constants, this is going to be temperature dependent. So based on the temperature, there is a K. So literally somebody had a bunch of water and they figured this all out by just having a water sitting around. But we want to talk about room temperature, our standard temperature. So this is the number you're going to use. So if I ask you what is the Kw, that's the number you're going to use. And most of the time we just write it as 1. So my Kw, which is equal to H3O+ times OH- is equal to 1 times 10 to the negative 14. I can then try to figure out what each one of these would be. Because if these two, kind of think about it like x times x has to be the 1 times 10 to the negative 14, that means that each one of these x's has to be 1 times 10 to the negative 7. This is going to be really helpful later. Okay? So now we have our Kw. So let's talk about what this means as far as what these numbers mean for these guys. And how do I know if a solution is going to be acidic, basic, or neutral? So OH3+ and OH- are present in all aqueous solutions because the water itself is going to create ions. Not that much, but something. Okay, so I have some options. I could either be neutral, acidic, or basic. So if I'm neutral, then that means that the amount of my acid ion has to be equal to the amount of my base ion. I have to have the same number. Which means at 25 degrees Celsius, if this is my Kw, these two numbers have to be the same. So that means that each one of them is going to be the 1 times 10 to the negative 7 concentration. Now let's talk about if I have an acidic solution. So say I add an acid. Acid is added to the water, like some HCl or something. So if I add acid, now I have more of my acid ion. So this is going to mess up my equilibrium. So what it does is my equilibrium is going to shift. Okay? It's going to shift to remove the H3O plus. So think about it as it's going to shift so that it uses up some of my H3O plus, which by default is going to use up some of my OH minus to go back to some of the water. So if I increase this is like Le Chatelier's principle from last time. If I increase this, I shift away, which means this goes and this goes to make some water. But what happens is, the way you can think about this is if this goes up, or we can look at it here, this number has to stay the same. This KW number can't change. So if this goes up, this has to go down to get the same number. Okay? So think about this like a balancing act. If this goes up, this has to go down because it has to always equal the same number. So what that means is that my H3O plus is going to be greater than 1 times 10 to the negative 7. And my OH minus is going to be less than 1 times 10 to the negative 7. If one goes up, the other has to go down. Because I have to keep that same KW. Alright, now let's talk about basic solution. If a base is added, so let's look here. If my base was added, this goes up, shifts away to make the water. So equilibrium shifts away to remove the OH minus, a new equilibrium is established. If this goes up, this has to go down. So now I'm going to have more OH minus, more than what it would be in neutral, less H3O plus. So now my H3O plus, OH minus, this guy has to be more than what it normally would be. This guy has to be less than what it would normally be. Because I always have to get them when they multiply together, it has to always equal the same number. So they have to work together. They have to work together. Alright, so we're gonna stop there just because I don't want to give you too long on your videos. So if you want, you can work with the next problem, but we'll start this next problem on the next lecture. I'll post up the next lectures for Friday soon, and I'll tell you what problems you can do for your homework. All right, stay safe, stay healthy, and you know what? No matter what, we're here for you. If you need anything, just shoot me an email and let me know what's going on. Come to office hours just to kind of hang out and say hi, like whatever you need, guys. I'm here for you. All right, bye.